So welcome to Math 140 Calculus 2. This is the last lecture of the semester. And again, what we're going to be doing is talking about applications of what we've done throughout the year, as well as, where can you go next? Now that we know all of this stuff, what would you do in future math courses? And so this is going to be a little bit of discrete mathematics. It's going to be a little bit of statistics. It's going to be a little bit of probability. It's going to be a little bit of multivariable calculus. So lots of different suggestions of what might follow. Okay, so this is a result of a talk I gave to a conference on teaching mathematics in Massachusetts a couple of years ago. It was inspired by something I did with my children back when they were 2 and 4, and then this was actually generalized and written up as a paper using my kids as well as some of the Williams students. So again, the goal is to show how you can get involved in research and problems really without too much. So one of the hardest things as a teacher is trying to decide, what should I teach? And I remember my first year at Williams, this was so long ago, we didn't even have Math 130, it was Math 103 back then. And my TA was surprised that professors actually get to choose what to cover. Now, there are certain things that you have to cover in Calc 1. If you do not cover differentiation, bless you, you're in trouble. Yeah, that's a given. But there's a lot of other things where, how much time do we want to spend on curve sketching? And when you consider the different tools that we have available, so much of the drudge work is now done automatically. You want to know enough so that you can understand, can you trust the result? Does it look reasonable? Has somebody maybe mistyped a number? Think back to the NASA probe to Mars, where one unit was in the English system, everything else was in the metric, and you now have a $25 million crater. Some alarms should have gone off that this can't possibly be right. So what I want to do is really want to talk to you about, how do you attack a new problem? How do you take something where we maybe don't have that much experience and say, well, what is this similar to? What have I seen that looks like this before? And how can I try to get a sense of what the answer might be? Okay, so general advice, always ask questions. This is a great way to find new research projects. Take something that's already known and see how far can you push this. Can you weaken some assumptions that are needed? Can you generalize? Can you apply it in a different setting? Try to gather data. The more data you have, the more chance you have of detecting a pattern. Most of the time when you start looking for things, you'll find garbage, or you'll find patterns that are fascinating that you can't prove. But with the power of computers, you can have so many different comparisons going on, you might eventually get pay dirt. Now, of course, you have to figure out what is the right way to look at the data. And that is a real challenge as well. I like to use games to get to mathematics. I think it's just fun. And there's a entire class you can teach on game theory. We saw a little bit with the basketball game, and we'll revisit that later today. And then I'll discuss, if time permits, implementations of some of these issues. All right, so this talk was given several years ago. It's been a while since my kids have been 8 and 6. This was done when they were actually 2 and 4. So the M&M game. So Cam, when he was 4 years old, asked me, if you're born on the same day as someone, do you die on the same day? So I thought this was a really good question for a 4-year-old. How do you explain randomness to someone, especially someone of that age? Well, one possibility is, okay, mom's an identical twin. Oh, look, mom's still alive. No, okay, so there's a lot of reasons why that would not be a good thing to do. That's not how you explain randomness to a 4-year-old. So we came up with the M&M game. When you have little kids and you want them to do math, if you can involve food, that's a really good way to do it. So the way it works is everybody starts off with K M&Ms. We did 5. And then you toss a fair coin all at the same time. If you get a head, you eat your M&M. If you get a tail, you don't. And you keep going until somebody is out of M&Ms. And you can see Kayla's playing against Cam, is playing against me. You can see my kids in the background. Does anybody notice anything about the M&Ms for Cam, Kayla, and myself? Yes. Yeah, what about the colors? Yeah, in fact, Kayla got all the blues. Do you think it actually matters what color you have? I don't, but when you're 2? What about Cameron? More than just that, though. It's a pattern. So he wanted a pattern. You think that matters? I took what I was left over with and I made the best pattern I could. It is almost 10 years later, and Kayla still talks about the game where she got 5 straight heads and got to eat all of her M&Ms as fast as possible. It is amazing what you remember. Okay, so what are some natural questions you could ask about this game? So I don't care if you can solve them. Just give me some questions you could ask. In what sense? We all start with K M&Ms and we keep going until only one person is alive. So who's going to die first? That's a great question. What else could we ask? Yes. We just opened one of the small little bags of M&Ms. And so I had a bunch of small bags. There may have been 1 or 2 extra M&Ms that the kids got to eat before the game began. So one is, who's going to die first? Okay, what else could you ask? You got to come up with questions. You got to be able to ask new questions. Good. How long will it take until the game ends? And the game could end with everybody dying at the same time. The game could end with one person still being alive. Good. What else could you ask?
Like the average amount of flips that it takes for someone to die.
So on average, how long will somebody be alive? So you could also ask, how likely is a tie? If we were to play this game, what is the probability? The whole point of this game was to show that just because you're born on the same day doesn't mean you die on the same day. And the number of M&Ms was trying to be a representation of how long you have to live. So what's the probability you tie as a function of K? It's also a function of the number of people you have. What if you have more people? What if you have a biased coin? Do you think the probability that everybody dies at the same time changes with the probability of the coin? If the probability of a head becomes closer and closer and closer to 100%, do you think it's more and more likely that you end in a tie? Yeah, because almost every time everybody's going to be getting ahead. So what's the dependence on the various parameters? Is there a way to write this down in closed form? So let's gather some data. So again, in earlier eras, we would actually have pennies. We would actually play this game and people would eat M&Ms. So you're going to have to just imagine that you're eating M&Ms. All right, we will do a run to lickety split. I will bring M&Ms if people want to put M&Ms on their ice cream. Just remind me when we do that. So here is a plot. The probability of a tie with just 1 M&M and 2 people is 33%, 19% with 2 M&Ms, 14% with 3, and so on. All right. Would you like more data or less data? More, yeah. Almost always the answer is more data. Sometimes it's red herrings that when you get too much data, you start to look at the wrong thing. Let's look at a little bit more data. So I gave this at the 110th anniversary of the organization. So I plotted the stuff up to 110. And then the question was, where do you think will be, and the next 110, where do you think will be at 220? So when you look at this, what might you estimate the probability would be at 220? Any thoughts? So you might think so you're saying it's approximately stabilized at this point.
Maybe like 0.025.
Okay, so where do you think it is right now? Maybe around 0.03. So maybe somewhere between 0.2 and 0.3. So where do you think it would be at 220? 0.025, so about the same. So the question is, we saw this in the German tank problem the last time. It was 1 + 1 over k that was converging to 1 for the slope. Do you think this is converging to a number greater than 1? I'm sorry, greater than 0 or converging to 0? Or is it tough for you to tell from this? Yeah. I think it's converging to 0, but it's really tough to tell you if this thing is slowing down. All right. So we'll see if this works. So if you see this formula, you can be happy that it's finite, but this is not a particularly pleasant formula to work with if k is large. I'm just trying to ask you, what does this look like for large k? Can you see asymptotic behavior? It's not so easy. So let's try to look at other ways of solving this game. We can represent this as a flow chart. So why do you think I'm going to have Cam represented with C M&Ms and Kayla with K M&Ms? Their names, right? You want notation so that you can quickly look down and see what's going on. Oh, C, Cameron, K, Kayla, got it. And so each of these happens 1/3 of the time. You go from CK to C minus 1, K minus 1, or to C minus 1K, or to CK minus 1. And so if I want to try to solve this, I'm going to just do K equals 4 rather than K equals 5 because it takes a while to just draw all this. So at any point, there are 3 things that can happen. I can decrease both of them. I can decrease just Cam. I can decrease just Kayla. And the probability of a tie is I have to end at the point 0, 0. So what is the only way I can end at the point 0, 0? Without first getting to, say, 1, 0, 2, 0, 3, 0, something like that. What do I have to hit if I'm going to get to 0, 0? Yeah, what? Well, that's one way. I have to hit 1, 1. If I don't hit 1, 1, there's no way to get to 0, 0. I could hit 1, 0 and then continue to play, and then Cam meets his last M&M, but the game is already over at this point. So I've got to calculate what's the probability I hit 1, 1, and then once I'm there, it's just going to be 1/3. And so each of these arrows represents an event happening with probability 1/3. And so this is a way to just calculate the probability. So without doing all the sums and whatnot, if you don't see this, I can actually create a flow chart, and for reasonable values of k, I can do this. Or I can even just program it for the computer. So let's start with 4, 4. So there's 3 possibilities. I can go to 4, 3, 3, 3, or 3, 4. Each happens 1/3 of the time. So now my probability of 1 is split equally among these 3 possibilities. Now for the next level, 2 of them actually could send probability back to 3, 3. So I first calculate that, and then for 4, 3, and 3, 4, I look at what it sends down. And now that I know how much is actually at 3, 3, I look at the probability it sends down. And so when you do it, you get 1/9 of the time you're at 4, 2, all the way up to 5/27 of the time you're at 2, 2. This is not hard. This is just carefully going through and saying, okay, each of these arrows happens 1/3 of the time. So for 4, 3, I send 1/3 of my probability, which is 1/3. So I send 1/9 of my probability at 3, 3. I send 1/9 down to 3, 2, and 1/9 down to 4, 2. And that's why 4, 2 is at 1/9. The reason 3, 2 is not at 1/9 is because it gets 1/3 of all the probability that goes to 3, 3. And then we just keep going down. And so, for the next one, I'm going to do the 2 ones on the outside first, and they'll go to, on the far left, 4, 1, 3, 1, and 3, 2. And then you just keep going like this. So it's just, tedious, not so bad. I get to 2, 2. Because if I'm at 3, 1, I could conceivably go, so I'll have to worry about those later. And I start worrying about those coming in. And then I finally find that my probability of being at 1, 1 is 245 over 729. And so then I just have to multiply by 1/3 for the probability of a tie. All right. So we've talked about the Fibonacci numbers before, and generating functions and solving the recurrence relation. So the Fibonacci is a recurrence relation of degree 2. I need 2 initial conditions, usually F0 is 0, F1 is 1. And then we have the beautiful Binet formula, which gives you an explicit formula for the nth Fibonacci. So this is wonderful. I can jump to, I don't have to calculate by hand the sum of the first 1,000 Fibonacci's or anything like that. I can just jump. And what we have is a little bit more involved problem now. So let's let XCK be the probability of a tie when we have Cameron with C M&Ms and Kayla with K M&Ms. So as long as C and K are greater than or equal to 1, the probability that Cam wins if he has M&Ms and Kayla doesn't is 100%. Similarly, the probability that Kayla wins when she has M&Ms and Cam doesn't is 100%. What if they both don't have, oh, so I guess, I'm sorry, so then the probability of a tie would be 0. And what's the probability of a tie if they both have no M&Ms? It's 100%. No one wins. And then we have the following recurrence. XCK is 1/3 XC minus 1K minus 1 plus 1/3 XC minus 1K plus 1/3 XCK minus 1. Each of these options happens 1/3 at the time. We have a recurrence relation. So rather than doing that flow chart, you could actually set up an Excel spreadsheet or something like that to just calculate stuff like this, or a little computer program to calculate stuff like this. So it's a clean way of reproducing the tree. Well, this required us to be intelligent and to recognize that there was a memoryless process. What if we didn't notice that? How many possibilities would there be? 4. All right, so let's say that there's 4, so each happens 1/4 of the time. What would you do next? So what should we do when you look at this equation? We have XCK equals 1/4 XCK plus 1/4 XC minus 1K minus 1 and so on. We could pull out the 1/4 from the right-hand side, but there's something better to do algebraically first. If you look at the left and the right-hand side, do you notice anything in common? We have XCK on both sides. Let's put all the XCKs, which we're trying to find in terms of the small things. XCK has C plus K total M&Ms. The other stuff has less than that. So if we bring that over to the other side, we get 3/4 XCK equals blah. So now multiply both sides by 4/3, and we regain the relationship we had before. So if you didn't notice thank you guys. So if you didn't notice the recurrence relation could be reduced using a memoryless process, if we did the algebra like this correctly, it would just magically appear, and then you'd go, oh yes, this must be telling me something, because that term drops out. Ah, that's right, I can just pretend that that didn't happen. Got it. And now these probabilities of 1/3 are very visible. All right, so we have this recurrence relation. I know x00 equals 1. So if I want to find x10, x01, those are 0 because somebody has an M&M and someone doesn't. So x11, I just plug into the formula and I get its 1/3. Now I can find x20 equals x02 equals 0 because somebody has M&Ms and someone doesn't. I can now calculate x21, which is the same as x12. I just use my recurrence formula and I plug in the x10, the x11, and the x20. And now I can get x22 by just plugging everything in. And you see how easy it is to do this. If you know the if you know the earliest stuff, you then get the latest stuff and you just march down. This is the power of recurrence relations like this. All right, so try simple cases and try to build intuition. So I'm probably not going to say too much about this. It is somewhat similar to a famous problem. You can take steps going either east or north, and you want to walk from the bottom left to the top right of a square without ever crossing the main diagonal. So you can hit the main diagonal, but you can't go above it. And the question is, how many ways can you do this? How many paths? And this is an extremely famous problem. It turns out it's related to how many valid ways can you put left parentheses and right parentheses so that as you read, you never have read more right parentheses than left parentheses. So it's like a valid way to group things. So it turns out these numbers occur all the time in mathematical physics. Well, what we're really doing here is we're doing something now where you have 3 options. Right. So over here, I'm just going to list a couple of the probabilities. So these are the probabilities of a tie when k equals 1, 2, 3, all the way up to 8. Does anybody notice anything about any of these numbers? 1/3, 5/27, 11/87, 22/45 over 21/87. So not a bad guess. I know it can't be prime because once I get to 245, that's not prime. Okay, but now for the bottom, multiples of 3. I can do a lot of math in my head. I've also given this talk before, and I will confirm that every denominator is a multiple of 3. Is it just a multiple of 3? Well, can you say something even stronger about the denominators? I'm sorry? What power?
Like squared, squared.
So what do you notice about all the denominators? So they're definitely multiples of 3. Are they all 3 to a power? Yes, they are all 3 to a power. Now you have to be a little bit careful because the pattern might be hard to see because I might be writing things in a very bad way. Maybe there's a nice power for the denominator, but what if the numerator has a power of 3? If I'm writing my fraction in reduced form, I'm actually dividing by 3, trying to be nice, but I'm actually confusing you by doing that division. It's actually better not to simplify. And this is something that might be a little bit hard to process after they drill into you in school, simplify your answer as much as possible. No, sometimes it's actually bad to simplify your answer because you lose the ability of just seeing what's happening. So what we can do now is we can multiply the denominators. And so I'm going to multiply by 3 to the 2k minus 1 to clear denominators. And now I get 1, 5, 33, 245, 19, 21, and so on. These numbers mean nothing to me. If they mean anything to any of you, you have a much better sense of number than I. What do you do if you have something that you don't know? So you want to find out something and you don't know it. What do? Yeah, you look it up. When I was a kid, this was not something you could do easily. You would have to go to, they call these libraries, and they had these things called books, or microfilm and microfiche. And I spent 4 years at Yale working in microfilm, microfiche. Now you just do a web search. I think I told you about my brother and his project on the Monroe Doctrine, or no? Yeah, where the teacher was surprised. You said you used a primary source. That would mean you would have had to look at Monroe's papers. Yes, I was visiting my brother at Yale, and Yale in microfilm has the complete works of Monroe. Oh, you do understand primary source. Okay, yes. Now you can just Google and get these on the web. It's amazing how much information is available. There's a wonderful website called the Online Encyclopedia of Integer Sequences, the OEIS. And what you do is you feed in a sequence of integers to it, and it will tell you all the sequences it knows. Now, if you start off with a very generic sequence, it's going to take a while before it tells you something. So let me see if I can. So I'll go to the OEIS. All right. So somebody give me a sequence of integers. Quickly, semester's ending. Okay, 1, 2, 3, 4, 5. Okay. So maybe I can do 1, 2, 3, 4, 5. So there are 7,228 results that start off 1, 2, 3, 4, 5. The first one is the positive integers. It says that's probably the one you were thinking of. And look at all the information it gives you about the positive integers. Well, okay, a lot is known about the positive integers. The next one is the non-negative integers. Okay, so it starts with 0. And then we have palindromes in base 10. Is that what you were thinking of?
Yeah.
Right. And then once you get up to 9, the next one would be 11, 22, 33. Right. And then numbers k such that 266 times 10 to the k plus 1 over 3 is prime. Starts off 1, 2, 3, 4, 5, right? You were torn between that and the palindromes. It's really, really hard to decide which of the two you had meant to. And so this is the power of something like the online encyclopedia. And normally you're not going to have 7,000 things, but if you do, what would you do if you have 7,000 possibilities? That's too many. What would you do? Add more numbers. And so the more terms you add, then eventually you would reach the point where it would hopefully just get one possibility. I'll just talk up to the screen. Okay. So when we plug that in here, it actually does say that the sequence exists. It's sequence A is 084771. Right. Which of course is, well, what is that sequence? And so, you can go online and look and see what does it tell you about that. So just a couple of takeaways. Always ask questions. A lot of times the hardest thing to do is to try to figure out, what do you want to study? If you ask the right question, you find something worth studying, tremendously valuable. Do I have a new statistic to look at that might give me a better prediction of whether or not my business is going to be a success, or whether or not I should be spending this much money on marketing, or this or that? There are many ways to solve a problem. It's not always clear what the best way is. Try something. If it works, great. If it doesn't, try something else. Different approaches will highlight different aspects of the problem. We saw one way of doing this, we all of a sudden have a memoryless process and the factors of 1/3 coming out. And that shows you something very different than viewing it as a walking problem. Experience is a useful and a great guide. Not surprisingly, the more things you do, the better chance you have of, I recognize that type of baby cry. I know what to do in this situation. You have to look at the data the right way. And as a rule of thumb, what's a good thing to try to do to data? Yeah, take the log. It should be something that's worth considering. Especially because it's so easy with computers nowadays to just say, take the data, do a log-log transform, and plot not y versus x, but the log of y versus the log of x, and see if that is going to be easier for me to just glance at and see what's going on. And again, relationships are incredibly complicated. It's often very hard to come up with an exact formula, but you might be able to come up with an approximate formula. And then the question is, when does that approximate formula really start to come into play? If you're trying to estimate, say, success in sports, at the start of the season, it's kind of hard. How do I know how well the team is going to do? Well, I might look at last season as a guide. And then the more games I play this season, maybe the less I weight last season and the more I weight this season. Or you're trying to understand how good is a player going to be? Well, maybe they're young, and so by getting a year older, they get a little bit better. Or maybe they're old, and getting a year older, they'll get a little bit worse. So I might have some bump for that. And then maybe for the first couple of at-bats, my model mostly predicts what they're going to do based on last year. After they've had 200 at-bats, okay, I think I've got a pretty good sense of who they are this year, and I'll probably put a very small weight on what happened last year. So experience can be a very useful guide. You need to figure out just how much to take into account. At what point do you say, if I give you a penny, what's your instinctive belief about the probability of a head? 50%. If I flip it 20 times and I get 18 heads, what do you begin to think? One is that it's weighted. There's another possibility. I'm sorry? There is, but it's extremely unlikely that for a fair coin, I'm going to get 18 out of 20 heads. So either the coin is not random or, and what? The flipping isn't. Anybody ever watch Penn and Teller Fool Us? So it's a wonderful show where magicians come on and they try to fool Penn and Teller, two of the greatest magicians. And there's one person who comes on and does a card trick. And Penn and Teller discuss it amongst themselves. And they say, because he's fooled them in the past. And they say, we don't think you fooled us. We don't think you did any trick. We think you're just that good that when you toss the cards in the air, you can just pull out as they're falling down the card that you want. And they asked him, is that what you did? He goes, yes. He'd been practicing this trick since he was a little boy, practicing it for 17 years until he could get good enough to do that. There are people who train themselves in how to toss a fair coin. Be very careful about what explanation you draw. You often do not know where math is going to take you. And so one of the things I really wanted you to see this semester is just what the options you have. Now, I hope you all consider math stats majors, or at least more classes in math stats. Always happy to chat to all of you about what can you do next. And even if you don't take any more math stats classes, if you ever see anything, hey, this looks like there might be some tool in math or stats that could help with this, Professor Miller, do you know anything related to this? Sometimes they'll say, yes, it's just blah, 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 blah. Or, no, but I have a Williams student who I know is interested in stuff like this and went off and is working at Amazon or working here or there. Let me pass this on to them. And then I will end for the last sentence of the semester with my favorite quote of all time, which you've heard many times. If all you have is a hammer, pretty soon every problem looks like a nail. All right, have a great semester. Stop recording.